Yeah, thank you very much for coming to the seminar. With like remembering all the schedule of your seminar in the afternoon. So remember that after the seminar we have some beers in the Agora. If you want to join us. So today it's a pleasure to introduce Stefan Talke, from the California Polytechnic State University. He's a visiting scientist here at the Physical Oceanography and Climate Group. And he will be talking about his research and his work here during these months. He has been here for already 2 months, but it's the end of his stay here, so sadly he will be leaving. So if you want to talk with him, it's
Oh, that's a lot better. Okay, let's see if I can get this to work now. Okay, perfect. So yeah, thank you very much. Thank you to Dr. Marcos for hosting me so well. And I hope that I will have the chance to come back here sometime. It's a very lovely place here that you have. I'm from California, and California also has a Mediterranean climate. And here's a picture of an area that people don't go to that often. It's the Sacramento Delta. And the picture really tells 1,000 words, but it also there's some things that it doesn't show. So for example, this is called Mount Diablo. We have a lot of Spanish place names for obvious reasons. On the other side of that mountain, about 50 kilometers further away, is San Francisco. So you can't see San Francisco, but in fact, the tides propagate from San Francisco all the way to this river. And you can kind of see that here because there's this line of foam from the algae, and it kind of goes up the rocks a little bit. I don't know if you can see that or not. So that's the action of the tides. Another thing you don't see here is that it was really, really hot that day. It was like going out into an oven. It was about 45 degrees Celsius, 110 degrees in our units, our strange units. But there's another thing that really catches the eye here. This is farmland. This is corn that's about 2 or 3 meters tall. Here's the water. Does anybody see the problem there? So basically this land is half of it it's peat. And so half of it is organic material. And over time, through the farming practices, it has basically oxidized. As I'll show later, there's also some subsidence going on in addition to the oxidation. And so being 6 meters below the water level is not a good thing, right? And one of the things, so I study water level and how it moves, how it changes over long time periods, and also short time periods from anything from turbulence all the way to hundreds of years. Water is one of these things that I know a lot of you are ecologists, but it's really a state variable. If you are wet or if you are dry, it's going to make a big difference to ecology. And then there are these intermediate zones where you're sometimes wet and sometimes dry. And those are often really productive ecologically. And we want to, one of the things I'm interested in is how is all of this changing with climate change, and how long, what is the duration? What are the durations of inundation, and how are they changing over time? So yeah, so the title says it all, but we'll get to there eventually. Just a little bit about myself. I did a PhD in San Francisco Bay. Working on an intertidal flat. Were a lot of contaminants in there. But you can see here's a mud flat that is sometimes exposed to air and sometimes not. A little bit further, there's a marsh that is inundated, but a little bit less often. Then I did a postdoc in the Netherlands. This is a very interesting case where it's a muddy, very, very muddy river. Has very low oxygen now because of all the organic material in the mud. But it wasn't always like that. It was, if you went there in 1950 or even 1980, it was a lot less muddy than it is now. The reason for that is channel dredging. They dredged the channel from 4 to 7 meters to accommodate big cruise ships, some of which have probably come into Palma. And it's a region where you would, why would you build cruise ships 100 kilometers from the coast? Well, it's just a historical accident. But rather than moving the harbor, they have dredged this river. And they've amplified the tides in some places from maybe 10 centimeters before 1900 all the way to more than 3 meters today. And they created this really good sediment trap which then depletes the oxygen. So that was really, really interesting. And that got me interested in this idea of long-term change, whether it's of tides, of sea level, or even ecological change or oxygen, things that matter for ecology. And then it was in the Northwest for a while. It's very pretty there when it's sunny. I would recommend you go. And then I study a bunch of things, and we all do, right? Okay, so what are we all know sea level is rising, right? It's rising here, it's rising in California. It's not always rising the same. There's very interesting dynamics, but some of the consequences are similar wherever you go. So we all are familiar with Venice, with flooding waters. Obviously, this is bad economically. There's nobody having a cafe when it's like this. But the same thing happens in Venice Beach in California. So when you have a high tide, it gets inundated, and it gets inundated for a certain amount of time. The question is how much time? And I'll show you that isn't the same everywhere you go, even for the same depth of flooding. And of course, we make maps like this and see how long, what will be inundated and for how long and so on. Again, I know that there are ecologists here. And one of the interesting things about the intertidal zone, so in other words, where it's sometimes wet and sometimes dry, is that there are very distinct bands of zonation. So I know you can't really see that here in Majorca because the tides are very, very small. But if you just go to the Atlantic coast, Spain, or anywhere, you have tides, and you'll find that the creatures and the plants, they all live in certain zones. So here you can see the mussels are, if they get too high, then they get dried out, they get desiccated, and they can't live. If they get too low, something else happens. Is the starfish comes and it literally sucks its guts out. It opens up the shell, and so they're controlled on the bottom and also on the top. And the starfish is also, it's not a fish, it's misnamed, but it's also controlled by the amount of time it's out of water, right? So as sea level rises, that's going to be a factor. But it also depends on the tides a little bit, and that's one of the things that I'll be talking about today. Also depends on the waves. And interestingly enough, ecologists haven't really done what coastal engineers do all the time, as far as I can tell, which is to look at how far up do the waves go and how far up does the splash go and how does that actually influence things. So there's a lot of little things that we could actually learn if we actually talk to each other, I think. So there's this paper from 30 years ago, roughly, showing that, in fact, things like the 18-year cycle in tides matters for the zonation or where you can find these mussels. So if you look at the paper, it matters that there's this variation in the tides, and so where the mussels are found can vary by 10 or 20 centimeters, and it varies seasonally as well. And it's the immersion time basically is a function of the tides, and the tides are always shifting seasonally over long time periods, and that's a control on the vertical zonation, and that's what this paper was about. So fast forwarding, right? So then there's this study, right? So this is an interesting study where in 1941 there were some college students, some 18 and 20-year-olds basically, that did a survey of this rock, and they fast forward. A graduate student in 2019 surveyed the exact same rock. And you can see it's the same rock. And here's where they did the survey. They did it, it's about 1 meter square. And so they did the exact same survey in 2019 and then try to figure out, are there changes over time? And you would think that there would be changes, right? We all know stories about, climate change causing big, drifts in the ecology. But in fact, there wasn't very much change. The only change was a slight shift towards warmer water species, but the sea level rise at that point doesn't seem to have a big effect. And here's some reason why. And so first, again, the area we're talking about is here, California. And if you look at California, these are sea level trends. I'll show you here you can see an inset with the actual trends, and you can see it actually varies a lot. And the reason it varies on the coast of California is tectonics. So especially if you go up to the northwest corner, there's some places that are actually rising up and some places that are going down. And that's, you could just think of it as, it's like a car crash, except it's two tectonic plates. And some parts of if you crash head on with another car, some parts of your car are going to go down and some parts are going to go up. So that's one way to think of it, right? And so here's about where this site was. And, first of all, it's not that much sea level rise. It's less than the global rate. And that's because the land is rising. But also you can see, if you take a look at the top graph, there's actually a lot of natural variability. And so in fact, in California, which may be one of the only states in America where we actually believe in sea level rise, we actually don't have that much sea level rise, especially compared to the natural variability caused by things like El Nino and so on. There's also a lot of variability over a year. So each of these lines is a different year. And if you compare, say, 1941 and 2019, it's actually not that much different. 1941 was actually an anomalously high year. It was a big El Nino year. But yeah, one thing you can take from this is, at least in Northern California, we're not outside of natural variability. So even if you have a little bit of sea level rise, we wouldn't necessarily assume that there should be a first order effect on the ecology. And if we take a look at the immersion time, so the immersion time is the opposite of immersion time. Immersion time is how long are you out of water. And so you can see that over time, depending on which gauge you use, you're kind of out of the water. You're in the water more often, so you're out of the water less often. So there's a slight downward trend over time. But this is a long time scale. And in fact, this might actually mitigate against some of the changes that you might expect from warmer temperatures and so on. Okay, so basically this study found it's very important to look at historical ecological data, but then it's also important to look at the physical factors and such as water temperature, which I'm not showing, and the immersion time, and see how they change. All right, so if you think about estuaries, so estuaries where the river meets a bay, saltwater meets freshwater, you can think of the same thing in terms of the vertical zonation, but rather than happening over a rock, like over several meters vertically, it happens more stretched out horizontally. So this is a Columbia River estuary, maybe 500 or 800 kilometers north of San Francisco, and you can see there's mud flats, and then the transition at higher elevations, you transition into marsh, and then there's wooded wetlands and so on, and they all can be mapped to a certain vertical elevation. So the question was, what happens with sea level rise? And you can actually look at a sudden sea level rise if you considered what would happen in a big earthquake. So again, this is one of those places where we're in the crumple zone of the tectonic plates. And each of these lines is a different subsidence, predicted drop in land level with a big M9 earthquake. And we know that'll happen. We know that the last one happened 320 years ago in the year 1700 or 1701. And we know that because there was a tsunami in Japan, and we can figure out from tree rings that it also came all the way over here. Actually, no, it was the other way around. There was a tsunami that was measured in Japan that had its origin in the Pacific Northwest. So you can see that there's up to about a meter or 2 meters of subsidence, and that's equivalent to many, many years of sea level rise. So the question is, what will happen to the ecological zonation? And we know that this was a really big thing 300 years ago, and it probably took a big disturbance. You can think of this as a big disturbance. It took dozens of years before the system re-equilibrated. So this is the mapping that an ecologist on the study did for different types of habitat that is currently in this estuary. And you could just take a look at it for a while, but there's quite a bit of variability. So there's sand flats, right? And then there's low marsh and there's high marsh. And you can see it's all interspersed. There's also forested wetlands and some shrub and some uplands. How will this change? And we ran, you can just do a simple thing where you just drop everything. but that doesn't really get at what really happens. You need to run a numerical hydrodynamic model and then see how do the tides shift as well, and how do datums such as mean high water and mean high water shift, because that's what the plants see, right? So when you do that, basically everything gets wiped out, and there's very, I think it's less than 2% of the habitat stays in its same habitat zone. And then even after it recovers, you see it's a much more truncated intertidal region, and therefore there's a lot less habitat. And the type of habitat that is there shifts a lot. So this is an example of what would happen with sudden sea level rise, but it's also spatially variable because it's tectonics. And so it's kind of an end member of what you might expect would happen if you don't have any sedimentation or morphological change. And that is, so it is a possible future. All right, so yeah, so that gets me to thinking about another area in California. And this is, again, the Sacramento-San Joaquin Delta. And here's some pictures from the 2023 year. This is about 100 kilometers from the coast. This is 160 kilometers from the coast. There was flooding in both cases. And the question is, are these actually influenced by sea level rise? And are they actually influenced by coastal processes? And we know that both of these places during low flow conditions actually see tides. So if you went and you did measurements, you would see that they are actually tidal. So just to show you, just to orient you, this is the place where that intertidal rock was. Here's where we were measuring the sea level rise. And this is San Francisco. So they're relatively close. And then this is the delta right here. Sacramento is up there. And so if we take a look at these two places, they're relatively far from the coast. If you went there, you would think, wow, it's hot here in summer. You would think this has nothing to do with the coast. But if you wait, right? So if you wait until 2 a.m. or 4 a.m., you'll actually get the sea breeze coming in. So they actually get some air conditioning from the coast. So you know that they're not so far away, even though they're at first glance not that connected. All right. So the main observation is that, in fact, water doesn't really know boundaries. It's all connected, right? Jurisdictionally and legally, this is where the coast ends, right? So in fact, the state of California, they made a law that anywhere west of here, you actually have to consider sea level rise in your guidance. And any city, any county has to make a plan by the year 2035, what they're going to do about sea level rise. Conspicuously, this whole area was left out, even though it's arguably probably one of the most sensitive areas because it's all below sea level. Also, in this area right here, this is where a lot of water gets pumped to the rest of California. So if this system floods, it actually puts into risk about the water for 26 million people, maybe 27 million. It's also, when it ends or when it breaks, it's also super expensive to fix it. So it's kind of like, some of you may be old enough to remember Hurricane Katrina. Well, before Hurricane Katrina, everybody was warning about that, everybody being scientists. And we're kind of like the Cassandras where nobody listens to us. This is another sort of situation like that. So one day you will see the news, oh my God, California is all flooding. There was an earthquake or a major flood and all these levees broke. Who could have known it would happen? Well, yeah. So just in terms of signal processing, here's the main problem that we're facing, right? So we know hydrodynamically this is all connected, but how do you actually figure out what the sea level rise is when you've got a signal that looks like this? So you can see here this sort of fuzziness here. Those are the tides during the low flow periods. And then these spikes here, that's not bad data. Those are river flow events. So that's when, you know, the snow melts or when there's a lot of rainfall. And you can see it's very intermittent in California because we have kind of like boom and bust. We have drought years. So like 2020 to 2023 were very, very dry. Some of the driest years on record. But then 2017 had one of the largest river flood events on record. So you can't just take a line and fit it to there and say, hey, we're done. And even if you take the low flow season, like if you just say, well, we're going to throw out the winter part of this series and we're just going to focus on summer, it doesn't actually completely work because there's still some effects. So what do you do to deal with it? I won't go into the details, but in fact, the red curve is what's called a non-stationary tidal harmonic analysis that takes into account the effects of river flow, both on the tides and on the longer signal. So you can take a look at Mate et al. If you're interested. But basically, we have to use some sort of way to filter out the effect of river flow. And if we can do that successfully, then we can maybe take a look at the residual and start to get some information about the sea level rise. So here's just another location. You can see again, it's very, very up and down. But if we take the difference between the red and the black curves, and then we filter it, and that's this purplish, this dark purple curve. You can't really, there's a lot going on here. I probably should have made a better plot. But here you can see the coastal non-tidal residual. So this is any fluctuations in water level, like daily fluctuations in water level that don't have an astronomical origin. So it could be caused by wind, it could be caused by some circulation pattern. That's what this magenta is, right? And so here you can see this is probably a storm surge. But if you take a look at this color, that's the filtered version, you can see that actually there's quite a bit of correspondence between the detrended inland signal and the coastal signal. And we can also see this in a coherence plot. I won't go into too much detail. We are still working on this. But the main thing is you can see different tidal bands, like 12 hours and 24 hours. You can see a weather band in the residual water level, even pretty far upstream right here. And then you can also see the persistence of longer time scale energy, which is kind of like the seasonal cycle of water level that you would see at the coast. And sometimes we don't see as much of a correlation as others. So yellow means it's more correlated, blue is less correlated. And that we think has to do with, well, it could be some residual river energy that's in there. It's also wind energy. It turns out wind is actually important in this area, and I'll show you that in a minute. All right, well, maybe less than a minute. So here is a climatology of wind that's measured right somewhere in here. And this area is very, very windy. It's hot inland, cool at the coast, and that drives a seasonal, but also daily wind pattern. And it really blows from west to east quite strongly here during part of the year. And that's this signal right here from roughly March or April all the way through September, October, and then it goes back down. You can also see it here in the wind magnitudes. And so that wind is blowing on the surface of the water and it's actually pushing it eastward. And so the further east you go, at least to about this region right here, you can get as much as 20 or 30 centimeters of water level difference just from the wind. That doesn't sound like a lot, right? Something like this. But if you're trying to figure out what trends are on the order of 5 millimeters a year or so, then that actually, you need to consider that signal as well. So here are just a couple examples of what we do. And so we can see that the coastal signal is actually correlated with the signal that we see after detrending for river flow. And if we remove that signal, then we can see that there's also a relationship with wind. So we're still working on exactly how to do this in the optimal way, but we can remove all these different factors and then try to see, do we get a sea level rise and is it coherent with what we would see at the coast? So this is the coastal daily water level variability at San Francisco from about 2003 to 2020. And we can see a trend, and the trend is around 4 millimeters a year right now. So that's roughly the same as global sea level rise at this point. So if you see something more than 4 millimeters a year, then that means there's something else going on, like the land is sinking. Or if it's less, then there might be actually uplift or some other factor like that. So here are just some examples, and they're just from all these different places. And if you look closely, you'll see some of the same patterns. Like here, you'll see this drop, and then this sort of increase into 2023. That's actually not an aberration. That's a big El Nino ENSO event that happened. And you can see that actually in all the different signals. Sometimes there's some sort of spike that we have to figure out what's actually going on. But by and large, we see a pretty good correspondence with San Francisco and with the coastal gauge. But if you take a look at the shape of these trend lines, you can see that they're all different. All right, so if we look at this for all the different gauges in this region, and this is actually a very well documented region. I don't know of any other delta in the world where there's so much publicly available data. We did an analysis of 50 gauges, and the main thing is, if you just look at it, all these are different colors, right? And anywhere from less than 0 millimeters a year of sea level rise to more than 10 millimeters a year of sea level rise. 10 millimeters a year is a lot. That means in 100 years it's 1 meter of sea level rise, even if you don't take into account the acceleration in sea level rise. And most of the locations are faster than what we measure at San Francisco. So what's going on? Well, this. So this is a paper that came out in 2018 by a geologist from UC Berkeley and then Manu Shirzai. This is one of these papers that really blew me away. You know, that doesn't happen that often where you say, wow, this changes everything. But this rocked my world. And what it's showing, and this is the south part of San Francisco Bay, it's showing that there's spatially variable subsidence and relative sea level rise on the order of like kilometers or even hundreds of meters. So we're used to thinking about sea level rise just at one location, and then we tell everybody who's building stuff, we'll use this sea level rise here from San Francisco. But in fact, that's not true. You know, if this is correct, and I believe some version of this is, it shows that you can have some places that are rising at 10 millimeters a year and others that are not seeing very much at all. So this means if you happen to be at the San Francisco airport or at Foster City, you have a big problem, and your problem is different than somewhere very nearby. And so there's different interests in a way, right? Like, how do you actually deal with something like this? You know, you can't just have a piecemeal approach, ideally, to dealing with sea level rise. You have to think about the whole system because there's going to be winners and losers. And if you take a look back at this result, it's exactly the same thing. On whatever spatial scale we look at, there's homogeneity in the sea level rise rates. This is particularly large here. And this is here, there's natural gas extraction. If you take a look at the telephone poles there, they're kind of like this because they're just kind of tilting over time. It's quite amazing. And then there's some areas where it's actually less than San Francisco, and this is because of tectonics. There's basically earthquake faults running all through this area. And that's, in fact, one of the failure modes here, too, is if a big earthquake happens. All right, and people have tried to figure out what the land subsidence is. You know, and this scale is in millimeters per year. You can see some parts of the Central Valley, so to the south of the Delta, are really going fast. You have to take this with a little bit of a grain of salt because this isn't the same subsidence that is affecting sea level rise. This could also just be oxidation of the land. It could be, if you see something positive, it could also be, well, people are building a road up or whatever. But all the indications are, yeah, that there is a spatial variation in vertical land motion. And we see similar things when we look at the gauges. All right, and yeah, so here, again, this is elevation 0 is probably around mean low water. And so you can see, and this is in our units of feet, right? So divided by 3, and you have meters, roughly speaking. So you can see, yeah, just this is very, very vulnerable. Okay, what else can we learn? Well, we can learn that other factors actually matter for water levels too. And again, who cares about water levels? Well, okay, it's what's actually setting the habitat boundary conditions, and it's setting the conditions for whether you're going to flood or not. This region right here, you have a lot of exports. So you can have up to 30 centimeters of drawdown in the water levels because they're pumping 300 meters per second of water. So literally in California, you have water coming in like this from one river. It takes a U-turn and it flows upstream and then goes to Los Angeles, which people in Northern California are not very happy about. But that's what it does, right? The rivers run backwards. There's other effects I won't go into, nonlinear effects between tides and river flow that matter. Coastal sea level propagates pretty far inland, and you basically see an effect almost everywhere. And then the wind is also really important. So all these things matter. And so, yeah, things get interesting when you go inland. They're different from the coast, and they're also different from what a river would be. They're somewhere in between. How am I doing on time? Yeah, doing fine. No, can't go forward anymore. Did it lose battery? There you go. Oh, okay, keep going. Perfect. Okay, so one thing that I'd be happy to talk to you all about is some of the ongoing work that we're doing on this, this region. Basically, there's a lot. One of the things that I work on is old historical records. There's a lot of records in this region, but actually all over the US and all over the world that are not being used. They're in boxes, they're in archives. Here's a list of some of them for this particular region. And we've digitized, I'd say, 2,000 years worth of data, and we're still processing it. But here you can see, you can actually get a really long time series of records. This is the San Francisco record. We did not do that. But you can sort of see some of these other records. And if you look at this one, right, you can see there's a divergence that happens in the trends. So some of these trends are really, really long term. One of the questions on one of the sort of hot topics right now in our field is this vertical land motion, is it constant over time or is it shifting? So long records like this actually could help us get information about that potentially. And I would think things, if this is being caused by something that is changing over time, such as water pumping, you would actually expect subsidence to be nonlinear. But it's a hard problem to figure out. All right. Oh yeah. So if we take a look at some of the really long-term results, we see a trend over time, right? So that's kind of indicative of sea level rise. This needs a much better analysis, but it's consistent with what we would expect. But this is very, very interesting to me. And this is something that we see actually in rivers and other places in the US that we have looked at. The Columbia River, the Hudson River on the East Coast. But basically in the US, and I would guess it's similar in Spain, we've created a lot of reservoirs over the last 100 years. And those reservoirs impound water, and then they let it go whenever it's convenient for people. And we also see changes in snowpack in our Sierra Nevada, and I would guess you see the same thing in Spain. And so that also changes the timing of when water will come. And so if you look at historical water levels, you'll see that the seasonality of them has changed a lot. So this is from 1911 to 1930, and you can see that water levels peak in sort of April or May. What's going on there is that's when the snow melts. So the snow melts, you have this big increase in water level, and then it collapses, goes down during the summer when we have our dry season. It's pretty much truncated now, and that's partly from reservoirs and partly due to changing snowpack and warming temperatures. So it's actually, this is another sort of first order effect on the delta and the wetlands that are in here, and it's something that we're trying to understand. The other thing that's not obvious in this is that, and we've seen this in other places, is that things like dredging and channel deepening and channel widening, and often what gets done for ships is it's natural river is really bendy. You just cut right through it, and you create a super highway in a sense for the boats. All of that actually also drops water levels. So we've got this kind of conundrum, and this is sort of where the edge of the research is right now, where in this part of the delta, so the eastern part, water levels have actually dropped over time because of the change in the river forcing and the change in how the river flow actually flows through the system. It's much more efficient to move water out of the system now than it used to be, and so water levels have dropped. At the same time, more recently, we measure the sea level rise and this change in sea level. And so at some point, those two are going to intersect and it's going to be a problem. But for now, people haven't really seen this problem yet in this part of the world. And that might be part of the reason why it's not being regulated or thought about. I'll just skip this, but yeah, I think in the interest of time, I'll just go forward. And the main thing that I want to show you here is that you also have to think about the infrastructure, right? So the levees in this case, those are the dikes that are holding back the water. The difference between that and sort of a high tide or some other measure of water level varies a lot as you go up the river. So in some places, there's a lot of what we would call freeboard. You can actually have a lot of sea level rise. And in other places, you have a problem. And these red colors here, that's not uplift. That means that the state has come in and they've actually raised the dikes between 2007 and 2017. Anywhere that there's blue, that's 2 LiDAR surveys, and it's the difference between them. And it suggests, okay, these levees are actually falling quite rapidly. It's not a problem yet, but this is another way of sort of proving that, hey, yeah, the tide gauges are actually measuring something that's real. All right, I'll just sort of interim summary. Sea level happens in inland waters. The effect it has is actually more complex than it might be at the coast, because you have to think about river flow effects, you have to think about infrastructure, you have to think about the history of the infrastructure. So the infrastructure may have been built to protect against a system that no longer exists. You know, and that's true in a lot of places. In Germany, for example, there are places where the tides used to be 10 centimeter, now they're 3 or 4 meters. And so you get amplification in tides, but you also have this change in the mean water levels. And so it's a very complex system, but eventually they're going to be influenced by sea level rise in quite a bit. And so it's a region that we actually have to think about. And we can get insight by looking at some of the older data. And inland cities, right? So, you know, an example in Spain would be Sevilla. Is that how you say it? It's maybe 70 kilometers from the coast, is my understanding. It probably should be considered a coastal city. And the same for Sacramento and Stockton in California. The same for other cities in the US, Baton Rouge in Louisiana, coastal city, Albany, New York, 200 kilometers from the coast, 250 kilometers from the coast, coastal city. A lot of places are connected through their rivers to the coast, and there's going to be sea level rise effects. And so that's something that is an area that we're currently researching, and stay tuned, I would say. All right, so let's go back and think about the immersion and immersion times and how they might be affected by sea level rise. So it's a little bit of a turn, a little bit of a difference, but it's kind of thinking about the same problem: is why does sea level rise matter? And these are 5 different time series, and you can see that the grayed out area is different in each of these locations. It's largest in Galveston, which I misspelled, and smallest in Boston. And in Boston, the tide goes up and it goes down very, very fast. It has 3-meter tides. In Galveston, you've got maybe 30 centimeter tides. And so that's this period up here. And so you might have an inundation of 20 centimeters that lasts for more than 10 hours in some places and less than 2 hours in another. And so that's another fundamental control, both on flooding for people, but also probably on ecology. And what are the tide properties that actually cause this. And so that's what I'm going to talk about for the next 5 or 10 minutes. All right, we'll just go. So a few years ago, I was thinking about this problem, and there's actually an analogy with an arch, and I'll just try to show you what that is, right? So an arch is, you can think of it as there's a circle. There's some point from which this circle is inscribed. And so here you can see this circle, and then there are these bridge piers, these columns, right? And you could actually draw a line across that. And something like this, right? And basically, what you can show through trigonometry, 8th grade trigonometry, is that the angle here is related to the radius, the location of the circle, and I think that's it. So basically, so that you can create a relationship between, you can figure out a relationship between the sagitta, S, so that's this riser, and the angle theta, and the radius, which we call, for tides, we call that amplitude. And yeah, so from trigonometry, we can figure out what this angle is. And then you just have to sort of go into the time domain. And remember that a sinusoidal wave, it's just going around and around in a circle, right? It's just going around and around a circle in time rather than in space. And so if we make that, if we just consider a sine wave with an amplitude, that's the radius, and a certain period t, and we put that into that equation, and let's see if it shows up, we can actually figure out what this angle is. And 2 times this angle is just the duration that you are above this threshold. So anytime you have a cyclic process, you can actually figure, and there's a threshold that's important, you can actually figure out how long that you're going to be above the threshold. And that's important for flooding, for tides, but hopefully I'll get to it. But that's important also for other biological processes and things that we care about. All right. So so what I did is I looked at tide waves all over the country, all over the US, and I fit a sine wave to them in each case. And so, in fact, this is actually, you could also fit a parabola. And basically, a sine wave and a parabola to a first approximation are the same thing. And interestingly enough, each one of these locations has a little bit of a different period that describes it. And there's some complicated reasons for that, but it's not what I would have expected at first. At first, I would have expected some are 12 hours and some are 24 hours, because that's the main frequencies of the tide constituents. So that's the main astronomical forcing, is at 12-hour and 24-hour periods. But actually, because there's both of those that actually mix together, and you get something that's in between. And you can take a look at the paper when it comes out very soon, if you really want to dive into the math, or we can talk about it over a beer. But observationally, you can see that there's this difference in the effective period, the compound period that describes each of these waves. All right, let's just move forward. Okay, well, here's the math. Just move on. So that suggests, right? So actually, if we take a look at this duration equation, right, we need to know a couple things. We need to know what the amplitude of the tides are. And what I did is I took a look at how does that vary across the US. In addition, we need to know what T is. That's this period that I was inscribing empirically into those measured predicted tides. And then we need to know something about S. S is, for this purpose, is the amount of inundation that you have. So 20 centimeters, for example, that was those, that's the inundation that I showed in those tide curves at those 5 locations. So if we take a look at this curve, at this plot, and you could take a look at Europe and you would see similar variations. You basically have a variation in the great diurnal range, which is the maximum minus the minimum tide each day. You see that there's very large variability. It's very, very small in the Gulf of America, and it's very, very large as you go further north. For example, in the Bay of Fundy or around Boston, you can get 5-6 meter tides, also in the Gulf of St. Lawrence. And also as you go up towards Seattle in the Salish Sea, you actually get 3 meter tides at some points. There's also a difference in what we call the form factor, and that's the degree to which the tides are diurnally dominated or semi-diurnally dominated. So if it's greater than 2, that means the tides are mostly once a day. And if it's less than about a half, it's more or less twice a day. And so you can see that there's differences in that forcing factor as well. And so both of these things, changes in amplitude and changes in the relative mix of the astronomical forcing, actually combine together to create the differences in the duration of flooding that we see. All right, so here's the definition of the form factor if you want to know. And so then empirically, but you can also show this theoretically, you can take a look at how these periods T that we use for this equation, the sine equation, vary all over the US and how they vary within individual areas. And it varies basically from 20 or 30 hours along the Gulf Coast to as little as maybe 12 hours as you go to, say, Portland, Maine, and then anywhere in between. It's also interesting to me that this factor varies by 10, 20, 30% within individual estuaries like Chesapeake Bay or San Francisco Bay. So this means that fundamentally, the duration of an inundation event is going to be different on small scales and on large scales. And this is another one of these things that might be controlling, things like, well, how long are you underwater? And that matters for a plant. It matters for if you're trying to get home as well. All right. So how does the duration vary for a 20 centimeter flood? So if a 20 centimeter flood happens, and this is for spring tides, this is for the larger tides that you might get in a month, the top 4% of tide events, basically, you will see that this duration varies a lot. And it varies because of all those subtle changes and differences in properties that I just talked about. But the take home is, not only does the Gulf Coast have some of the highest sea level rise rates, we'll see that in a minute, but when they get flooding, they get flooded for a long, long time. But then you also see variations as you're going up the coast. You see variations of a factor of 2 within an individual estuary as well. So again, this is just for 20 centimeters, so not a lot. You can consider that a minor flood. But it's also something that's shaping the ecology. And so it would be really interesting to talk to an ecologist in Chesapeake Bay, or even here in San Francisco Bay, or up near Seattle. What does this matter? I don't know, but it's something that that we see. All right. So finally, sea level rise. So now we get back full circle to sea level rise, and again, the interesting thing about sea level rise is that it's very heterogeneous. And there's some reasons having to do with the ocean circulation and gravity and so on for why ocean sea level is different. But it's also because of subsidence. So this is relative sea level rise. And here, again, in California, you see this sort of effect of plate tectonics. Here in San Francisco Bay, we see what's happening even as you go further eastwards. And again, this shows that we actually really need to think about river flow effects so that we can actually monitor these regions. And you also see anywhere you look, basically, any sort of scale that you're looking at, you see differences in the sea level rise rate. It's almost like a fractal thing. So sea level rise, right? So the next thing that I did is think about, okay, so what if you were about to flood, right? Like you had a tide and it's just about to flood. Now let's project the sea level rise forward and figure out how long will it take at a linear rate of rise. Actually, I included a little bit of acceleration. How long would it take until you get to a 2-hour inundation event? And so that would be something that might be, something that you would notice, something that might actually be important regionally for infrastructure or whatever. And not surprising, you see variations, quite a bit of variations all over the US, anywhere from a year to maybe as much as 87, almost 100 years in some places. So the transition time to a long duration flood is quite variable depending on where you are. And so these are just also things that we need to think about. Usually when we're thinking about extreme events, we think about how high it gets, but in fact, it also matters how long you're underwater. And so that's what this shows. And this analysis is only for tides. One of the things one could do in the future is also consider how does a storm surge event mix with a tide event. And when you look at measured water levels, so this is this curve here. This is Hurricane Sandy, one of the biggest floods in the last 20 years or so. You can take a look at how long is it over a major flood threshold. And in fact, it's just a mixture of this wave, which is the predicted tide, and this wave, which is the storm surge wave. And if we model the storm surge as a parabola or as a sine wave, and we mix it with this wave, we actually get this red wave. And it pretty well models what actually happened and gets the duration of the flooding to within 10%. So we can gain insights through this approach with the tides to understand how long do storm surge events happen as well. And one of the things that, just next time that there's a storm surge, just listen to the weather forecast and see whether they say how long is it going to flood. They probably won't. It's just a blind spot, I think, in our forecasting even. You might say, well, it's going to be, well, in our country, they might say, oh, we might expect a storm surge of 4 to 6 feet, like 2 to 3, 1.5 to 2 meters, but they don't tell you how long it's going to be or when it's going to happen. And all that information is there, but it's just not something that we're necessarily thinking about. All right, how am I doing on time? Okay, I'm almost done. Well, I'm not almost done, but we are almost done. So just as a final thought, and I won't go over these slides, but there's a lot of other cyclic processes that you could think about. This is water temperature, right? And this is in 2 different locations. And you can see, you can model the climatology of water temperature also by a parabola or a sine wave. And that's what's being shown here. And a lot of these places actually have trends over time. And here, this is, and a lot of the time, there's a threshold that matters. So this is the Willamette River near the Columbia River mouth. And it's showing the number of days above or below a threshold over time. And you can take a look at this paper if you want. It's from 2023. And basically, it's showing that the number of days over a warm water threshold, anything over 20 degrees is bad for salmon, and it gets regulated, is actually increasing over time. And it's also, if you take a look at it, you did a climatology of this, it would also be a sine wave. So if you have a trend and you have a sine wave, you can see how the exceedances will change over time using this approach that I did. And I think with that, I'll just say, yeah, you can do it with ERA 5, but we can look at that the next time I'm here. All right. All right. Thanks for listening. And yeah, hopefully that was good.
Stefan?
Sure. Are there any questions? I know I went a little over. Yes.
Thanks, Stefan. Very good indeed. Yes. I have 2 questions.
Sure.
You had some slides on which you showed that water levels up in the river inland, the variability in the water level, co-varied with the non-tidal residue.
Okay.
Where do the non-tidal residue come from?
Yeah, so that's the I didn't have time to really explain that. So when I showed it was covariant, that was with the coastal non-tidal residual. And so what that is if you take a station that's not related, that's not within that region. So I was using a tide gauge 30 kilometers or 40 kilometers from San Francisco. Then you take a tide prediction and you take that out of your hourly data. Then what you're left with is what's called the non-tidal residual. And so I took out, in addition, the sea level trend from that. And so what you have then remaining is just fluctuations that have to do with coastal processes. So it could be El Nino, it could be wind, coastal wind. Yeah.
Some of those variations
Yeah.
could actually be related to river flow, like hydrostatic.
It could.
Or baroclinic one.
And
Not necessarily barotropic, but some of them
It-
will actually influence sea level on the coast.
yeah, and so I've looked at that a little bit, and the way I looked at it was to see if there are any tide effects with river flow. So so in San Francisco, which gets used as, it's one of the longest Pacific gauges, and most of the time people don't think of it as a river flow gauge. But in fact, you can show that the tides there react quite a bit to river flow when it is there. And because and in fact, using the approach that we're using, you can show that you can get up to 10 centimeters of water level variability directly from the river flow. At the coastal station I used, you don't see any correlation. That doesn't mean that there isn't any effect. Like Chris Pykuch had a
I'm
paper.
not talking about only
Yeah.
phase of the tide. I'm talking about the freshening of the water in the coastal zone. That
Yeah.
will lead to baroclinic effects. maybe?
Yeah, I mean, there could be some. It's not going to be, I don't think it'll be huge though.
No, yeah, well, I don't.
It might be a
I
few
don't know.
centimeters now and
Maybe it's
then.
good to ask Chris.
But yeah,
But also some of the trends in sea level rise that you could see in the tide gauge, especially if it's close to the river,
Mhm.
the river mouth, could be actually due to the river flow, right? Not
yeah,
necessarily to say dynamic or ocean processes, right, I guess.
yeah, that's always something that one has to consider.
Yeah.
And to the, I don't remember exactly, I mean, to the best of what we can see, that in San Francisco, the long-term decrease in river flow might have a couple of centimeters, 1 to 2 centimeters of effect. The same is true when I looked at Astoria, which is actually on the Columbia River. It's further inland, it's 20 kilometers from the coast, so much more river affected than San Francisco. Interannually, it's definitely affected quite a bit by river flow, and so is San Francisco. But if you take a look over the long term, the actual, you know, the actual effect on the trend is relatively small, at least for these locations.
Yeah, there is a very nice paper by Chris Pykuch.
Yes, I like that
where he
paper.
shows also that it's in really like that actually. So he looked at some tide gauges and he showed that the long-term trend in those tide gauges, a large portion of the trend was actually driven by changes in the river flow.
Yeah, I don't know about the Platte. I know that for the east coast of the US, he had a very nice paper that looked at how variability year to year had a lot to do with whether it was a high flow year or a low flow year. But I wonder, well, anyway, the mechanisms might be a little bit different on the east coast, because you have the Gulf Stream, and we don't have that. And what on the West Coast, we're really affected by upwelling a lot. And I don't know to what extent that's going to interact with the river flow at the location where the gauge is. It's a very good question. And yeah, my assumption right now is that it's noise, extra noise in the signal, but it would be very interesting to find out whether it's actually important.
Second question.
Sure.
It's about the subsidence rate that you show. You have the map that blew you away. You said based on INSAR data.
Right.
I think this map was based on 4 years of data, if I remember correctly.
It's not a long data set.
It was in the past. Do you have an updated map based on more recent data?
That would be.
It's a short period, so I was wondering whether if you calculate the rates based on a longer period with a.
Yeah, so that's a really great question. I mean, those weren't my papers. So it would be great to ask Manu and see if he could update that for us.
They do have updated.
They might.
They are producing now updated maps.
Yeah, and I mean, those maps are very tricky. I think they are indicative. They indicate something is going on, but I don't completely trust them, to be honest. Because like if it's based off of a correlation or they're being constrained by GNSS, which if you look at GNSS, it's very, very noisy. And in this region, there are things like micro earthquakes or earthquakes that happen over 4 weeks or 6 weeks. And how do they account for that in the GNSS processing? I've asked them what they do, and this was 5 years ago, and they said, well, we just assume that we take it out, but we just assume that it comes back. I don't know what if you take a look at the different, there's 3 or 4 groups that are processing GNSS. If you take a look at their answers in this region, sometimes they're not even within the confidence interval of each other. And so that is going to impact what you get out of INSAR. And INSAR itself is a very complex processing game. And different groups don't always agree with each other in the answers they get. So what I take out of it is that this is actually a great opportunity for us to make tide gauges more useful, so that and to use, basically, I think we need an all of the above approach, right? So we need, LiDAR is probably a better, if we had repeated LiDAR flyovers locally, we would probably be able to get a better estimate of what subsidence is. All that we have in the Delta is one from 2007 and one from 2017. And I don't know, you take the difference of 2 numbers, you get an answer, but you don't know how statistically good they are. And if you have processed LiDAR data or you've worked with it before, you know that, yeah, they say it's a 10 centimeter RMS error, but it can be a lot more. Anyway, this thing about measuring water levels and actually measuring land levels is a surprisingly challenging and difficult thing. And it's really, really important. And so, yeah, I guess I'll just leave it at that. But there's a lot of work to be done and a lot to be learned.
It's a bit late, so maybe we can stop here and continue the discussion on after. Yeah, thank you very much.
All right.
Thank you.